Hello everyone, I'm Han Junhee. In this video, we'll implement a feature that performs 3D pathfinding based on SVO. We won't use a separate template, we'll create a C++ project. First, let's create a new level and save it. Next, in Project Settings, set this level as the editor's default map. We also need to create a collision trace channel for the SVO. I'll name it SVO Obstacle. Set the default response to ignore. All SVO collision checks will use only this trace channel. Next, let's create the SVOVolume class. Choose Actor as the parent class. I'll keep the code organized in an SVO folder. I'll leave only the constructor and clean up the rest. Since the volume needs a location, I'll register a scene component. Let's define the volume size property. Next, I'll define max depth, which sets how many times the octree is subdivided. By default, the octree will exist as one large voxel. Its depth is 0. If the octree overlaps part of an SVO obstacle, it can't be a valid path, so we'll add 8 evenly sized child nodes inside it. These children are smaller, so they can double the path resolution. That makes the depth 1. Placing octree nodes locally, only where needed, like this is the key feature of an SVO. Now let's define the collision channel and the debug flag. Next, we'll create a struct to store the SVO nodes. A node can store information, such as its depth. Here we will use only 7 bits. Next, we will store whether this node is a leaf node using 1 bit. This way, the two properties will use only 1 byte in total. Since the number of nodes can grow quickly, we use bit fields to reduce the struct size as much as possible. Next, we will store the node's actual position and size. Also, the octree needs to know its parent and children. A node may have no children because it is a leaf node, but in this project, octrees blocked by an SVO obstacle will not be created at all, so that case also applies. Now let's go back to the SVOVolume. Create an enum class that represents the octree state. As I mentioned earlier, we won't create blocked nodes. We'll create a method to build the SVO. Additionally, we'll create 2 more methods to use in build SVO. One is a recursive function that actually creates the nodes. Since this is a top-down SVO, we'll recursively create child nodes down to the specified depth. The The second method checks whether it collides with an SVO obstacle. Now let's declare properties that include the node array and root index. Query parameter is defined as static to prevent reallocation while checking many nodes. Now let's define the methods. First, considering rebuilds will initialize everything. Next, get the root location and half size. Also check whether the root is colliding. If it is colliding, we will keep subdividing the octree. The length of one side of a child is half of its parent. We will create a node array to receive the recursive function results with the same size as the number of children. Also, to merge the child nodes, we need to receive the root index of each subtree. We will process this in parallel. Now we will calculate the child locations. With an octree, this is easy to get using binary numbers. Child index ranges from 0 to 7. Here, 0 can be represented as 0, 0, 0, and 7 as 1, 1, 1. In this way, if we view it in binary, it is like getting 3 booleans. Assuming each boolean is bound to x, y, and z, if 0 means minus from the center and 1 means plus, this gives us the position of that child. Now we'll run the recursive function at each child position. ParallelFor generally distributes work evenly across workers. However, with an SVO, work tends to concentrate in specific areas, so if one task takes a long time, it can become a bottleneck. To prevent that, we'll set it to unbalanced, making the work scheduling more flexible. Once the child build tasks are complete, we need to merge them all. First, we'll calculate the total. Then insert the root node into the node array. Now we'll iterate through the child results. If a child's root index is not valid, we can treat it as non-existent, like blocked, so we won't collect it. Make it continue from the end of the node array. Now we'll merge the subtree into the nodes array, but we also need to update the parent index of the subtree nodes. To update them, we need to iterate through it, so first I'll get the length of the nodes array and then merge them. Right after that, we'll iterate through the added nodes and update their parent index. We're done with the mixed case, so let's move on to empty. In the empty case, there are no collisions, so it will become an octree with only a single root node. Then, of course, the root node becomes a leaf, so don't forget to turn on isLeaf. Now that we've filled the entire nodes array, I'll update the node count. Now that we've made everything, let's implement the recursive build function. Each execution of this recursive function will create one node. Its behavior will branch depending on the collision test. If it is empty, we will create only one node, and that will become a leaf node. In this case, we do not recurse. First, let's implement the empty case. We need to get the node's half size. With the total size and depth, we can calculate it easily. Next, we'll run the collision test. If the collision result is empty, we'll insert the leaf node into outnodes and return the index. Create the termination condition based on depth. If the code reaches this point, it means there is a collision. It could be blocked, meaning fully blocked, or mixed, meaning partially blocked. But as I mentioned earlier, we're not going to handle blocked. I'll explain why when we implement test occupancy. We'll create a mixed node. This is not a leaf node. If there is a collision, we need to create 8 child nodes. Just like when we implemented build SVO, we'll use Octree indexing. We'll also call the recursive function for the children and increase depth by 1. We'll iterate 8 times and add each one as a child. But we need to check whether at least one of the children is a valid node. The only valid cases are an empty node or a mixed node with children. If all child nodes go down to max depth without being empty, they will all return index none. That node can be considered blocked, so we won't create it. Since we don't need blocked, we'll delete the node we created and return index none. Now let's implement test occupancy. Here, we'll test collision using the size of the octree. Now we'll return empty or mixed, depending on whether there is a collision. We're not checking whether it's blocked, but it could actually be completely blocked inside. The way to check that is to run additional tests inside at a smaller size. But build node recursive is already doing that recursively. Also, since most of the SVO area is empty space, it's important to finish the collision test for empty in a single pass like this. Now let's create a method for SVO debugging. All nodes are in the node array, so we just need to iterate through it. We'll separate the colors based on depth and draw a point for leaf nodes. Call this at the end of build SVO. Additionally, to make things more convenient in the editor, we'll set it up so the build runs automatically when the level starts or when a property changes. Next, let's create a Pathfinder class. It will inherit from Blueprint function library. Create this in the SVO folder as well. Let's create the findPath method. Agent radius ensures that only paths the agent can traverse are returned. Here, we'll also perform pathfinding using the Lazy Theta method. For that, we'll create a line-of-sight helper method. We'll also create an entry to use for pathfinding. Since we'll use it in a priority queue, we'll override the comparer as well. Now we'll implement the method, but before that, let's create a few methods we need. We'll create them in SVOVolume. The first one is the FindLeaf method. It will return the index of the node at a specific location. Next is the GetNeighbors method, which will return all neighboring nodes adjacent to a node. Lastly, let's create a getter. First, if the position is outside the volume, we'll return index none. Now we'll move down step by step from the root. And our destination is a leaf node. If it's not a leaf node, it will have children. We can easily get the child position using Octree indexing, just like before. We know that relative to the center, front is 1 and back is 0. Using that, we can express it like this. With the child index we calculated, we update node index as we go and find the leaf node. Of course, there may not be a child at that position. In that case, return index none. If node index is a leaf node, the loop will exit, so return it. Next, let's implement GetNeighbors. We'll initialize it and validate it. Pathfinding will only go through leaf nodes. If it is not one, return. An octree has neighbors in 6 directions, plus XYZ and minus XYZ. We need to iterate through all of them and collect the neighbors. First, let's find the actual position to check. A vector struct can be accessed like an array. In XYZ order, they are 0, 1, and 2. Set the direction to side and move slightly farther than half size. Then position will be located outside the octree. We'll do this for all 6 directions. Now we'll get the node at position, which is similar to FindLeaf. The difference is that the neighbor we want is not just a leaf node, but one of 2 cases. One is a leaf node that is the same size as or larger than the current node. The other is all descendant leaf nodes of a neighboring node with the same size as the current node. Of course, we'll collect only the adjacent leaf nodes, not all of them. So the node search only needs to repeat until it reaches a leaf or until the depth matches the current node. Once we get the neighbor node index like this, it will be one of the two cases mentioned earlier. If it's a leaf node that is equal to or larger, we'll collect it right away. Next, we need to collect all adjacent leaf nodes of the neighboring node. On one face of an octree, you can always see 4 children. If we know the 4 child indices on the face adjacent to the neighboring octree, we can access those adjacent child octrees. Since these children also share the same adjacent face direction, we can repeat the same 4 octree indices down to the leaf nodes to get what we need. First, let's create an array to store the 4 octree indices. Here we'll use fixed allocator. It can store only up to 4 items, but since there's no heap allocation, it's lightweight to use. Of course, you can use a C-style array as well. But for convenience, I'll use this one. Next, we'll define axis mask. Axis mask will be used to get indices only along the axis direction we want. For the x-axis, it returns 0, 0, 1, for the y-axis 0, 1, 0, and for the z-axis 1, 0, 0. This is the same approach we applied to octree indexing. Next is axis bit. If side is -1, it returns axis mask. If it's +1, it returns 0. Using this, we can get all children on a specific directional face. For example, if you want all nodes where the x-axis is negative, we just need to collect every index where the first bit is 0. Also, right now axis bit points to 1 when side is negative. That's because when the current node faces the positive direction, the neighboring node is adjacent in the negative direction. Now we'll iterate from 0 to 7 and collect indices based on whether the target axis is 0 or 1. Next, we'll traverse the tree to collect all leaf nodes. For convenience, I'll implement it with DFS. Here we'll use inline allocator. This is similar to fixed allocator, but the difference is that it switches to heap allocation if it exceeds the set value. Now let's go back to Pathfinder and implement the method. In FindPath, we'll handle initialization and validation first. Next, we'll get the nodes located at the start and end positions. We'll clamp the agent radius and access the node array. For this pathfinding, we need to verify whether the target can actually pass through. We could simply compare the octree node size with the agent radius. But this may not be suitable in certain situations. For example, if the agent radius is 700 and the octree in an alley is arranged as 200, 400, 200, even though it could pass through the octree with a size of 400, it wouldn't be able to use it. So, we'll perform the collision test ourselves. However, running a collision test every time would be too expensive, so we'll only run it when agent radius is larger than the node size and cache the result for each node. If no collision test has been performed, it is 0. If there is a collision, it will show -1. If not, it will show +1. Now let's create a lambda for this. Naturally, if the start and end nodes are not traversable, pathfinding is impossible. Also, if start and end are the same node, there is no need to run pathfinding. Next, we'll proceed with pathfinding. First, create arrays to store the cost and parent. Since all nodes are managed as an array, we don't need to use a hash table. Next, we'll create the open and closed arrays. Closed is a Boolean flag for every node. We could just use a bool, but here we'll use a bit array. Since it uses a bit mask internally, it's efficient for cache and memory. Now we'll heap push the start node into open. If you manage elements in an Unreal array using only heap push and heap pop, you can use it as a min heap tree. Now we'll run the pathfinding, and since we'll update the neighbors on each search, we'll declare the neighbor array outside. Next, we'll get the neighboring leaf nodes and keep only the passable nodes. First, if loss fails, we'll perform a recovery step that uses a valid nearby node as the parent. A valid node must have closed set to true, and among those, it must be the closest one. After reconstructing the path, we'll check whether the node has reached the destination. The reason we reconstruct the path before validating the destination is that a loss can fail even at the destination node. To reconstruct the path, we just need to trace the parent array repeatedly. There is one edge case we need to handle here. It concerns the node after start and the node right before end. The current loss check only uses the center of the octree. As mentioned earlier, the node after start also performs loss against the center of the start node. However, the LOS between the start vector passed in as a parameter and the node after start can fail. To ensure this, we'll also perform an LOS check between the start vector and the start node's center. Now let's move on to the next branch. If we get here, it means the LOS succeeded, but we haven't reached the destination yet. so we'll search the neighboring nodes while keeping the current node's parent. Of course, with this optimistic loss check, we'll set the neighboring node's parent to the current node's parent. This works because when the neighboring node is popped, we immediately validate the LOS. We've already implemented it, so the parent is restored if the LOS fails. Now that everything else is implemented, let's implement the LOS method. The LOS method will simply perform a collision test. Since we implemented pathfinding using the Lazy Theta approach, LOS calls are relatively infrequent. So here we'll focus on a simple implementation. It can also be implemented with a ray marching technique using SVO, but considering the code complexity, the performance gain was hard to notice, so I'll use this approach. In this video, we'll profile SVO performance with Unreal Insights. In general, if a method has the uFunction macro, the profiler can track it. For other methods, you need to add a dedicated macro. Lastly, I'll add the macro to the relevant methods. Go to SVOVolume. I'll add one to FindLeaf. Next is GetNeighbors. Add it to build node recursive as well. We'll also check test occupancy. Add it to lows in SVO Pathfinder as well. Now the code work is done. Let's close the editor and build. Once the build is complete, launch the editor. First, I'll set the floor mesh collision to collide with SVO obstacle. Next, I'll create a BP actor that inherits from SVOVolume. I'll place it directly in the level. Then, as you can see, the SVO will be generated. There are fewer Octree nodes in areas without collision. On the other hand, you can see the Octree subdividing where it collides with the floor. To demonstrate pathfinding, I'll place a sphere. Set it to movable and set the actor tag to start. I'll duplicate one and set it as target. Next, I'll use cubes to create a complex path. For testing, I'll make this movable as well, and make it collide with SVO obstacle. Now I'll create some complex terrain. Once that's done, we'll call build SVO and find path in the BP. First, I'll find the two spheres. This isn't the usual approach, but for testing, I'll run the build and pathfinding on tick. I'll enable Stet FPS to check performance. Now let's run the simulation. You can see it finding a valid path through the leaf nodes. Even though it's running on tick, the frame rate isn't low. If I move the sphere, it immediately returns a different path. As I move the wall, you can also see that the build updates quickly. Next, let's look at the pathfinding responsiveness for a large object. As the actor gets larger, you can see it finding another traversable path. Of course, if it is too large, it cannot find a path. As I mentioned earlier, let's check how long it takes in Unreal Insights. Of course, I turned off Draw Debug for the test. With the simulation running, I'll capture a trace. This should be enough, so I'll stop the simulation and check the profiler. If we zoom in on the game thread, we can see how long build SVO and find path took. They took 700 and 300 microseconds, respectively. At the bottom, you can see build node recursive recursing 6 times, equal to the depth. Also, the foreground worker and background worker process build node recursive in parallel. The game thread waited for all workers to finish their tasks. This time, I'll raise max depth to 8 and test it. They took 14 and 4 milliseconds, respectively. Normally, you wouldn't run this feature on tick, but you can adjust the values to fit your requirements. Finally, let's compare what happens when using a regular loop instead of ParallelFor. I'll leave max depth at 6. Unlike the previous 0.7, this came out to 1.9 milliseconds. Of course, it doesn't use any other workers. For simple repetitive tasks like build SVO, parallelization can be a good option. But it does make the code more complex, so choose based on your requirements. Thank you for following along with this long video, and thanks everyone for watching.